All right, guys. Here's another problem. Example 4. What are the dimensions of an aluminum can that can hold, again, 40 inches squared of soda and that uses the least amount of aluminum? So when we hear the word least, they're telling us they want us to minimize the volume, all right? No, not the volume. They want us to minimize the aluminum. So this would be considered the material, and we're gonna say the surface area, right? Because that's what's being aluminum is what's containing the soda in it. So they want us to minimize the materials used, and the materials are being used to create the surface area to hold this soda. Assume that this can is cylindrical and capped on both ends. So you see the picture here. First thing you want to kind of consider is, well, what is um, the formula for the surface area, right? How do we get the surface area of this aluminum can? Um, and that formula is going to be 2 pi r squared plus 2 pi r h. Okay? And just to kind of give you guys a little, explanation of where the 2 pi r squared comes from, that's from your lids. You see that's a circle, pi r squared. That's the area of a circle, and you have two of them on the bottom and on the top, all right? And then if you were to cut this container out and stretch out that center wall, you're gonna have it's gonna be 2 pi r in length all around, because that's the circumference of a circle, right? That's the circumference of a circle. And the height is going to be h. So the area of this section is going to be 2 pi r h. Okay, that was just a quick little tutorial where that's coming from. You could always work it out that way too if you forgot the formula. So what are the dimensions of an aluminum can that has a volume of 40? Well, they're telling us the volume is 40 inches cubed, and they want us to figure this out, right? Well, what is the volume? Do we have a volume formula? What would be the volume? Well, isn't that just the base, the area of the base times height, right? So the volume formula is just going to be our base pi r squared times height, and we know that's equal to 40 inches squared. Okay. And we have another formula, surface area. So we have this formula and we have this one. But they want us to minimize the amount of aluminum. So we want to work with this formula. But we notice that it has what? It has R and H. So to make it simpler, we should explain this equation in terms of one variable. So what we're going to do, just like in the past examples, we're going to solve for one of the variables. And it's just up to you what you want. I decided to go with R. Let's solve for, I want to have the surface area explained in terms of the radius, because that's obviously a big part of the problem. Like if you're talking about the volume of a cylinder, the radius is important. So I solve for H so that I could replace my H in the surface area formula, and everything's going to be in terms of R. So what is H? Well, if I divide both sides, I'm left with H is equal to 40 over pi r squared. Okay. Now I'm going to plug that into my equation, my surface area equation. Okay, you guys see that? H, right? Replace that with that. And I'm left with 2 pi r squared plus 80 over r. All right. And since we're trying to minimize it, we're going to take the derivative of this function, okay? And I shouldn't say S. That's actually incorrect. Now it's going to be my surface area equation. I could label it SA, but I should put the derivative out here, okay? Or I could also label it S with respect to R, because we're solving in terms of radius. Regardless, when I take the derivative, I'm going to end up getting 4 pi r minus 80 r squared. And again, this is kind of like the last example we did. I think example 3. So look into that if you're having issues with it. No, actually, it was example 2, I believe. It was example 2. Okay. So I have the formula, and what we're going to do is we want to make it equal to 0, right? So when I make it equal to 0, what am I going to be left with? Well, if I just move 80 over r squared to both sides, or 4 pi r, we're going to be left with this right here. And I'm going to solve for, that should be r, okay? Multiply r to both sides and divide by 4 pi. If I multiply r to both sides, r squared to both sides, and I'm going to divide both sides, right? I'm just doing it at once because I'm running out of space. But if you were to do that, you're going to be left with r cubed is equal to 80 over 4 pi. And that's a number, okay? That's a number. You can plug it in your calculator. And I have to take the cube root of it to really get r. And that's going to be the size of the radius that will minimize the surface area, right? And what is that? That's actually about 1.853 inches, right? And we could show why it's a minimum. I'm not going to show it. And the good thing is that since we've already been doing it, we know that you take the derivative, it gives you a max or min. I'm not going to show that it's a minimum, but if we were to plug in numbers to the derivative equation, we would see that there's going to be a little, again, just kind of like the little concavity, right? So we got r, but they said they want the dimensions. So what's the other dimension? Well, the other dimension is going to be h. And how do I get h? Well, the good thing is that we already have an equation where we have solved for h. So if I plug in my r, and again, at this point, you could probably just use this approximation, and it'll be okay. It's not going to be exactly equal to. If you want to be more precise, then yeah, you should use the cube root of 80 over 4 pi. But the approximation is fine. And that gives us a height of 3.707 inches. Okay, so there you go. That gives us our dimensions, where r is 1.85 and the height is 3.7 for a container that holds a volume of 40 cubic inches.